Okay, hi. Good morning, everyone again. Welcome to ABL's market briefing for December 2022. Thank you ever so much for the people who are in the room today. Wasn't easy getting in this morning for many of us. So big shout out to those of you taking industrial action. Appreciate that. And the weather, that didn't help either. The briefing that we're going to be giving today is accredited by the Chartered Insurance Institute, and delegates can claim up to 1 CPD hour for their participation. We will therefore keep a record of those of you logging in online as well, and those of you in the room. So if you need a certificate to back up your attendance, then please do let us know and we can get that sent to you. My name's Mark McGurran. I'm the Global Managing Director for Maritime here at ABL Group. And today I'm very pleased to be introducing our presenters. Giving the technical presentation will be Jasper Gaskin. Jasper recently started on our graduate development scheme, and he's a graduate engineer with a university background in mechanical engineering, and he's based here with us in London. Following that, Cindy Rosensteel will be giving the case reports for last month, and Cindy is a consultant electrical engineer who recently joined our London office from our New York branch. She mainly focuses on engineering for the offshore wind and renewable industries, and we'll be hearing from when Jasper's done with the technical presentation. The usual caveats apply, Chatham House rules apply, and the information contained in these presentations and any opinions or comments expressed are those of the presenters and not necessarily those of ABL. We'll be taking questions later on the technical section, but not on the case reports, because obviously some of those are still ongoing investigations. At the end of today's briefing, whether you're online or with us in the room, if you can take a few minutes just to fill out the survey that we've got going. This is really important for us because it helps us keep and develop our CPD accreditation, which is important to some of you. And it also means that obviously we can actively look to improve the services we offer, and we can make sure that the briefings match your requirements and your needs. Before I hand over to Jasper, I would just like to remind everyone that ABL Group is a signatory to the Neptune Declaration on Seafarer Wellbeing and Crew Change. And even though COVID seems to be further and further behind us, seafarers are still often working longer than they're meant to due to some ongoing crew change issues. And there are a multitude of other factors which impact this, of course, globally. Many of my own colleagues at ABL Group come from a seafaring background, so crew welfare is something that's very close to our hearts. And this is why ABL Group some time ago decided to sign up to be a signatory to this declaration. And I would please ask that if any of your organisations are able in a position to sign up to this as well, that they do so. It really is very helpful. So with that bit of housework done, I'm going to hand over to Jasper, who's going to do the technical presentation. Thanks, Jasper.
Okay, good morning, everybody. Thanks very much, Mark, for the introduction. Very happy to be here today presenting to you all. And yeah, thanks to everyone in the room for braving the weather and the extremely cold weather. I thought my ears were going to fall off this morning. Not to be dramatic. So without further ado, yeah, my topic today is renewable energy sources, the importance of research and development in the clean energy revolution. As these briefings are CPD accredited, a very important criteria of this is to run through our learning objectives for today. Today's learning objectives are as follows. 1, you'll be able to identify the current energy trends, comparing projections of energy production to energy demand. 2, you will develop an understanding of clean energy legislation and what it means for the industry. 3, you will be able to explain the importance of research and development in unlocking potential offshore renewable energy sources. And finally, you will be able to summarize the risks and hazards associated with offshore renewable energy installations. I will go over these again at the end of the presentation. So this presentation will outline the current energy legislation and goals that are driving the transition to alternate energy production. The importance of research and development of renewable technology in achieving these goals will also be discussed, with a focus on tidal stream energy. Finally, the associated risks and hazards of offshore installations will be highlighted, and ABL Group's role in these topics will be touched upon throughout. So to introduce this topic, I want to talk about the current trends in energy generation and consumption. The graph on the right shows data from the International Energy Agency 2020 report of Renewable Information Overview. Here, the worldwide historical growth and future projections of primary energy consumption by fuel type is captured. Looking to the right-hand side of the dashed line, These US-based projections depict that renewables will become the primary energy generation source worldwide by 2050. I should note that the near linear growth rate emphasizes that this is a fairly simplified prediction. Of course, other sources will increase their output to keep up with the rising demand during this period, but at a lower rate. If this projection of renewable energy taking over as the primary generation method is to become reality, what is it that we must keep up with in terms of our energy consumption? A harsh dichotomy to these renewable energy projections is presented in the graph seen on the left. From the Energy Information Administration, we can see that global energy demand is on an exponential rise, with 2020 levels in Asia set to double by 2050. Of course, this is not news to any of us in the room today, but for renewable energy sources to take over in the race to keep up with our global demand, the following questions are raised. What can be done between now and the prophetic 2050 marker that so many governments and international bodies have set as our next environmental milestone? What advancements and improvements in technology must be made in this time? And finally, is it even going to be possible? So how can we best illustrate the contest we're currently facing between our energy production versus our demand? Well, I thought there's no better way to describe potentially the biggest problem we're facing right now than through a cartoon. So the cartoon on the right depicts a race, which itself has infinite laps, in which we have our energy demand forever in first place, with its foot firmly on the accelerator. The lagging racers, renewables, oil and gas, nuclear, to name a few, are constantly fighting to keep up with the demand, overtaking, undertaking, and sometimes cutting corners to do so. How then do we create the image we see here, with renewables overtaking its competitors and tailing our demand? The components of renewable energy generation must be modified and improved, much like our renewable cars components. The graph on the left from the International Energy Agency shows the average annual growth rates of renewables supply from 1990 to 2020. We can see many components: solar PV, or the engine of our car, wind, the chassis, and biogases, the drag reduction system, are currently the best performing parts of the renewables car. But what about the tires, gearbox, steering wheel, airbox, and so on? Small 1% improvements to each of these components may not make a notable difference in isolation, but together they compound into improving the overall performance and endurance of our car. So each must be developed to its full potential. Clearly, there's room for improvement to allow the top speed to be pushed further and further, particularly in hydro, geothermal, and thermal energy storage. So, how can we act against the clock to improve these? Before getting into current renewable technologies and the importance of their advancement, I just want to give you an historical overview of some of the legislation that is driving this transition at a political level and what it means for the EU, the UK, and ourselves at ABL as well. So a bit of a historical background. In 1992, countries joined an international treaty, the United Nations Framework Convention on Climate Change, as a framework for international cooperation to combat climate change by limiting average global temperature increases and prevent dangerous human interference with the climate system. The Conference of Parties, or COP, was established as the supreme decision-making body of the UNFCCC. By 1995, countries launched negotiations to strengthen the global response to climate change and, 2 years later, adopted the Kyoto Protocol, which legally bound developed countries to emission reduction targets. Today, the UNFCCC has near universal membership, and the Kyoto Protocol has since been replaced by the more commonly known Paris Agreement. The Paris Agreement was adopted by 196 parties back in 2015 and requires economic and social transformation. It also works on a 5-year cycle of increasingly ambitious nationally determined contributions, or NDCs, which are each country's climate action plans. On the screen are some examples of NDCs set by the UK and the EU. In terms of how these goals have translated for us at ABL, we are currently working towards a target of 50% of group revenues to be generated from renewables by 2025. Although climate action needs to be massively increased to achieve the goals of the Paris Agreement, the years since its inception have already sparked low carbon solutions and new markets. So bringing us into the present, most recently in COP27, which lasted almost 2 weeks and ended on November 18th, produced 5 main outcomes. The first is that the need for funding for loss and damage was finally admitted to the agenda for the first time, after developed countries have long sought to avoid direct talks on financing loss and damage. This resulted in about 340 million euros of new pledges. The second is that the influence of oil and gas interests at the climate talks is growing, with a 26% increase in registration from lobbyists from the oil and gas industries at COP27 compared to COP26. Thirdly, concerns that current net zero targets are not rigorous enough, and in the words of the UN chief, have loopholes wide enough to drive a diesel truck through, have meant that net zero targets have been made stricter to avoid greenwashing. This is the act of making unsubstantiated claims about the positive environmental impact of a product. Before now, food and farming has been a topic which has remained absent in UN talks, even though global food chains from production to consumption contribute to around a third of greenhouse gas emissions. This year, flooding in Pakistan saw rice harvests plummet by about 31%, while drought caused yield losses in the US, Europe, China, and India. This prompted the Food and Agriculture for Sustainable Transformation, or FAST initiative, to be established. And finally, the technology mechanism was established in 2010 by the COP to facilitate technology development and transfer to developing countries. This year, a work program was launched for this in order to accelerate the deployment of transformative climate technologies. So this final outcome of COP27 brings me to discussing some of the hottest and latest renewable technologies that have been or are being developed today. There are, of course, more types of technologies being developed than those you see on the screen, but for the purpose of this presentation, I'm going to touch on wind and solar and then focus on tidal stream. Firstly, we have wind technology, which can be constructed onshore or offshore with other technological variations. Pictured in the top right, we see one example of many concepts for airborne wind energy generation, and to the left, some different types of offshore wind. From left to right in this image, we have a monopile, jacket, and tripod for the fixed installations, and then a semi-submersible tension leg platform and spar for the floating. As for solar, it is also a front-end developing technology. Panels can be categorized into types of first, second, and third generation, each trading off between cost, efficiency, flexibility, carbon footprint, and manufacturability. Floating solar farms will play a key role in enabling countries with limited available landmass to meet their net zero pledges and leave land free for agricultural activities. Large-scale solar farms are currently taking off in Asia, powering millions of homes from rivers and lakes. Building integrated photovoltaics is coming further to the forefront of solar technology and incorporates sunlight energy capture into building materials themselves. This means roof tiles, window glass, facades, and shades all generate electricity to supply to the designated building, saving land space that would otherwise be used for solar farms in the process. And finally, onto the main topic of my presentation today, we have tidal stream technology. The three technologies you see on the screen are some of the major tidal projects that have been implemented in the last couple of years. The orbital O2 on the far left captures tidal energy at the water's surface, where water speeds are highest, and is said to be the most powerful tidal turbine in the world for its size. The CIMEC Atlantis Energy AR-15 turbine and Maygen project you see to the right are both promising endeavors in the tidal world. These installations hold one crucial drawback in common. The turbines are so big, around 20 meters in diameter, that they can only operate within bodies of water which are energetic enough to produce power from them, operating at upwards of 3 meters per second stream velocity. And so they are restricted in their remit of geographic deployment. So perhaps counterintuitively, does this mean that smaller designs will produce greater energy yield? Tidal energy offers a predictable, reliable, and theoretically unlimited source of energy, which the exponentially increasing worldwide demand is crying out for. So how can we increase its viability and therefore better the performance of our renewables racer that we saw before? There are more than a few factors to consider in the bid to sustainably increase current renewable energy generation, to modify our renewable car as much as possible. These include progressing renewable energy policy mandates, increasing grid stability, capacity, and architecture, ensuring consistent increases in installed capacity to drive down costs, and, for the purpose of this presentation, most importantly, technological advancements through research and development. In this part of my presentation, I'm going to exemplify the importance of research and development in unlocking more of the Earth's potential renewable energy, and will use my own university dissertation as a form of a case study. So there is massive potential for communities to power their lives using the ocean, which could generate well above 130,000 terawatt hours of electricity per year, according to the International Renewable Energy Agency. The UK government estimates that wave and tidal stream energy combined has the potential to deliver around 20% of the UK's current electricity needs, which is around 30 to 50 gigawatts. Unlike solar and wind, tidal is a predictable and reliable source of renewable energy, as the motion is constantly driven by gravity. However, due to the limitations I just mentioned, tidal technology currently lies far behind its renewable competitors in terms of development due to its highly site-specific nature. Lower velocity sea regions, that is between 1 to 2 meters per second, are far more prevalent throughout the globe. Therefore, the design of tidal stream turbines to accommodate these sites could improve the overall global feasibility of tidal technology. As part of Cardiff Marine Energy Research Group, the work I carried out during my penultimate year at university was part of a British Council research project. This project looked at utilising small-scale tidal stream turbines in areas of low-velocity free flow. So the work itself presented a structural analysis using a form of finite element analysis software on a new twin-blade 4-meter diameter tidal stream turbine to operate in low-energy bodies of water in the Philippines. This design will likely be implemented within a cluster of floating turbines. To begin, results from a previous fluid dynamics software analysis were taken to accurately simulate the forces that the turbine would experience in operation. With these forces known, I then analysed if the turbine could operate successfully or if it would fail miserably under the tide's load. To do this, I identified the stress, deformations, and safety factor that the blade experienced over a range of turbine rotating speeds and water velocities for a turbine made of structural steel and then one made of aluminium alloy for comparison. The graph on the right shows the effects that changing the turbine's operating speed and design lifespan have on the design safety factor. For the purpose of this study, the parameter of main focus was the safety factor. Defined as the ratio between the ultimate material stress and the maximum stress actually reached in operation, the safety factor gives the likelihood of failure of the turbine over a given design life. This means when the safety factor is less than 1, failure is certain to occur before the design life is met. According to the engineering toolbox, rotating turbine components should have an overall safety factor within the range of 2 to 3, meaning for safe operation within a given design life, the maximum recorded stress within the turbine should be 2 to 3 times smaller than that's maximum allowable material stress. So, is this design going to work safely? As with most endeavors to advance our current technology, this one was not as fruitful as I'd hoped. I concluded that safe operation was not possible for the design with the chosen materials, as my best case safety factor was still some way off the lower limit for that of safe design. However, promise was shown towards safe operation over a 25-year design life, with further research and development needed. Potential was shown in the movement towards small-scale tidal turbine technology and insulation into the abundant low-energy marine areas around the world. As for future recommendations, I touched upon the importance of further research and development in this study, given the potential benefits of its success. My future work suggestions included further breakdown of the blade structure to increase result accuracy, further investigation into the behaviors of different materials and metals being used for the design, with the possibility of incorporating internal support structures, development of a full environmental impact assessment, or EIA, prior to the front-end engineering design, or FEED package, and finally using both CFD and FEA software in a two-way fluid structure interaction to accurately hone results. I hope this element of my presentation wasn't maybe too technical today, and I also hope it's given you some insight into how close the next technological step can be for renewable energy systems. I believe the importance of funding and training to support research and development in accelerating the renewables race is just as important as the speed with which we implement new installations. This is perhaps a bit of a backwards analogy, but to chop down the tree of traditional energy generation, It's important to keep the axe of renewable energy as sharp as possible. On the topic of tidal research, I'm just going to touch upon some examples of what's currently going on within ABL Group. So ABL Group's marine energy engineering consultants at INOC in France are already working on implementing small-scale tidal turbines with developers Nova Innovation. Since 2016, Nova Innovation have been installing a turbine array in Shetland. This array now consists of 6 turbines, each of 9 meters diameter, and is currently powering around 600 homes. It's the world's first fully functioning tidal array and boasts the most turbines. The developers worked with Tesla also to add energy storage to their tidal technology, creating the world's first grid-connected tidal power station with the ability to deliver baseload power and energy on demand to meet consumer needs. Nova also have an array being constructed in the Bay of Fundy in Canada, which is home to the largest tidal range in the world. The technology here, much like that in my research project, is focused on small, extremely reliable turbines to bring down the cost and frequency of maintenance. Nova claims that its current array can operate for 18 months without intervention. And if you weren't already convinced on tidal energy, Nova Innovation apparently has plans to produce Scotch whisky distilled by tidal power in the Sound of Islay off the coast of Scotland. INOC have also contributed towards a project on the EU's Research and Innovation funding programme, Horizon 2020, titled Effective Lifetime Extension in the Marine Environment for Tidal Energy, or ELEMENT programme. The goal of this project, led by Nova Innovation, is to reduce tidal energy costs and increase installation lifetime by optimizing the control system of a tidal turbine. The diagram on the right shows the existing tidal turbine control system elements in blue, with additions made in this project seen in green. The idea here is to develop and validate an innovative control system using the turbine itself as a sensor. Behavioral modeling and artificial intelligence will be used to optimize performance and deliver an adaptive control system that will slash the lifetime cost of energy by 17%, making the EU tidal energy sector commercially viable. The overall budget of this project is in the region of €5 million, and INOC's main contributions included computational modeling of the turbine, work on the gravity-based structure, which is pictured in the bottom right, from initial design to construction and testing, and finally, assessment of tidal potential in France, which involved evaluation of socio-economic, regulatory, ecological, and human impacts. Other work conducted at INOC includes turbine foundation design, numerical modeling of tidal turbine performance, blade shape design, mooring analysis, and installation stability analysis. If you'd like any further information on these projects, please email myself and I can refer you to our experts in INOC. So, knowing where I'd be delivering this presentation today, I knew that in the process of trying to draw a complete picture of my chosen topic, I could not go without talking about the risk associated with some of the engineering I've touched upon. Of course, as with any engineering operation, there are risks involved in renewable energy installations. I'm going to finish now by presenting some risks and hazards in offshore energy in particular. Understanding the risks and hazards associated with the engineering and construction of new technologies in the renewable realm are still in their infancy, particularly where natural catastrophes are concerned. With the introduction of new tools and technologies comes the new challenges in construction. Offshore renewable projects involving tidal, wind, and solar farms pose significant challenges to insurers responsible for underwriting these risks. Larger, more complex projects mean bigger potential losses, while the threat of natural disaster looms large. As for tidal, risks arise from vessel collision, which applies to most offshore installations, blade damage or corrosion as they are fully submerged in the ocean, and unexpected impacts from marine wildlife. It should be noted that risks can also arise from the birth of new technologies. As with all new designs, when they are first implemented in the field, reduced operational capacity can often bring claims resulting from loss of income for operators. This can be caused by reduction in operational capacity pending completion of remedial works, or for permanent loss of income if the defect cannot be rectified. In solar power, risks to insurers include microcracking in panels, which can be extremely difficult to find in a farm of thousands of panels. These can worsen over time and weaken energy production. This issue can arise in any stage of a panel's life cycle: manufacturing, installation, transportation, and are common claims in the market. Upon lightning strike at a location, insured parties can put forward a claim. However, how can a loss adjuster check every panel and identify how many of them have actually been damaged? Production can also be seized via structural or electrical failure of panels caused by moisture ingress, saltwater corrosion, stability problems, electrical or mechanical overload, or impact from airborne animals or objects. And finally, in wind, offshore wind farms face various risks, including weather conditions, maintenance costs, innovation challenges, and environmental and political considerations. The most pressing of these from an insurance standpoint are damage or destruction from hurricanes, improper maintenance of components causing turbine failure and in some cases generating heat or sparks and igniting flammable materials. Of course, the immediate marine environment and inhabitants must be considered in construction also, which is often carried out in an EIA prior to FEED work. Finally, general hazards when working on offshore installations include falls from height, mechanical hazards, blade failure, ice throws, ship collision or men overboard, electrical hazards, and finally, as I mentioned before, fire or explosion of turbines or vessels. Though the desire to quickly accelerate renewable energy production is clear, the obligation to first evaluate associated risks should not be forgotten. So, to finish, let's recap on today's learning objectives. Firstly, you will be able to identify the current energy trends, comparing projections of energy production to energy demand. Secondly, you will develop an understanding of clean energy legislation and what it means for the industry. Thirdly, you will be able to explain the importance of research and development in unlocking potential offshore renewable energy sources. And finally, you will be able to summarize the risks and hazards associated with offshore renewable energy installations. Hopefully, these outcomes have been met for those of you in the room today and online, and I hope you found this presentation insightful. Are there any questions? You're also welcome to email them across to Ellie later on. No, no questions. Okay, I'll pass over to Cindy.
Jasper, you're so tall. I have to adjust this. Hold on a second. Hi, everyone. I'm Cindy. I'll just go to the next slide. Oh. Yeah, so the purpose of this section of the briefing is simply to keep you updated on some of the recent higher cost incidents that ABL have been involved in. And in doing so, show you, or at least remind you, of the sorts of incidents and casualties that can happen in shipping and marine operations. But in case you haven't attended these briefings before, you might be asking yourself, what are these so-called case reports? Well, to answer that, these case reports feature largely, but not exclusively, hull and machinery casualties with estimated costs of repair in excess of $250,000, usually excluding salvage costs. They cover only a subset of the total ABL Group caseload, typically in the order of 10%. However, this is an important subset because it represents about 25% of the H&M cases by number, and around 65 to 75% of the H&M cases we survey by cost. Treat this with caution, though. Estimated costs are often preliminary and are subject to further inspections and/or investigations. In presenting these case reports for the last month of activity, it's not to attribute blame. We just aim to convey what happened. So we won't be giving any definitive conclusions about the cause, as many of these cases are still fresh and it wouldn't be appropriate for us to do so. And in many cases, the cause is still under investigation anyways. And as for most engineers, we want to focus on the numbers, so let's start off with some statistics. So here's an overview of November 22 proportions by number. We've been notified of 17 high-cost cases during November, and the dark blue columns in this graph shows the proportional distribution by casualty type. There were 4 machinery and grounding cases, 2 fire, collisions, and heavy weather cases, 1 propeller, flooding, and loss of anchor cases. With such a small sample set, you're bound to have gaps in the distribution that you can see when you compare it to that of the distribution for a whole year. In this case, the whole of 22 given in the green columns. Despite the small sample set for a month's worth of higher cost cases, you can see that the distribution still reasonably follows what is, year on year, a fairly consistent trend with the more common casualty types being populated. And now here we've added in the distribution of these same 17 cases by their total costs. And we'd like to point out that the fire cases this month are nearly 3 times as significant by cost than they are by number. And this is not unusual. Some casualty types are just more prone to higher magnitudes of loss. The total estimated cost for the 17 cases is about $19 million, and that makes the average cost of the high cost cases for November just under $1.2 million. This is a bit higher than the typical annual rate of about $1 million per high cost casualty, when individual extreme cases of over $50 million are excluded. Now at this point, we normally go on to look at the developing totals for the year. However, as we're so close to the end of the year, we'll leave that till next month when we have the preliminary totals for the whole of 2022 to show you. And now let's get to the fun bit and look at the selected casualties. We've only selected 10 of them, and that's if we have time to go through them all. So first up, we have this 15-year-old products tanker that was involved in a glancing blow-type collision while departing a Middle Eastern port at about 3 o'clock in the morning. The other vessel was inbound on the fairway, and both pilots had communicated and agreed to passing each other in a standard port-to-port configuration. For some reason, however, the other vessel suddenly deviated to port, and despite efforts to get out of the way, our vessel here got hit on her port side aft. Nothing dramatic in terms of damage, fortunately. If you look closely here, you can see the disturbances to the side shell and bulwark. And then in this next image, on the boat deck above has been bent downwards. And here, you can see the provisions crane and platform have been impacted by this collision. We haven't got the full story yet from the other vessel, but if you were looking for a root cause in incidents like this, you would be looking at possible things like navigation equipment failure, steering system failure, loss of power, or navigational error. And next up, we have this elderly cruise ship that had been tied up at the berth while waiting for about 2 weeks to go into the dry dock we see her in now. At about 2:30 in the afternoon, the day before she was due to enter the dock, she was caught in sudden high winds that broke her mooring lines and caused her to drift off the berth, bow first. She ended up hitting an LNG tanker that was tied up on the other side of the basin. This is where she was moored, and you can see the remnants of some of the mooring lines. And this is the LNG ship that she hit. Incidentally, this is the vessel that had caused the delays and had just come out of the dry dock. And this is how they met. It wasn't a high impact contact, and there was only fairly minor damage to the side shell of the LNG ship caused by the prow of our passenger ship, which you can see just on the right side of the picture, just below main deck level. And here on the left is a picture taken by the crew of the LNG ship just after the contact. You can see the corresponding slight damage to the prow of the passenger ship. That wasn't the only damage to the passenger ship, alas. On the right, you can see where her back end, her starboard side, contacted the corner of the quay. And actually, there were several impacts resulting in dents and one breach that we can see now that she is in dry dock. Now, you might be thinking they hadn't tied her up properly. But apparently she had more ropes out than were required by the yard and the local port authority. The high winds were actually forecast for much later on, overnight, and the crew had been in the process of adding more mooring lines when the high gusts of up to 66 knots hit them. And this is a good reminder for us all that weather forecasts are not always fully reliable or accurate, especially us in London know this. And having said that, our attending surveyor told me we should look on the bright side of this casualty. He tells me that, had our vessel not hit the LNG ship, she would probably have been blown further across the bay and ended up aground on rocks. So there's always a silver lining. Of the 2 fire cases we have this month, one seems to be an old familiar story, while the other is something relatively new. First, we'll start with the familiar. Probably of the order of $5 million worth of damage to the 7-year-old bulk carrier that suffered a fire in her generator room while entering port under pilotage. Not necessarily the most impressive or efficient of firefighting responses by the crew, perhaps with a quantum of loss, but the fire was put out, fortunately, and there was no injury to personnel. The main engine escaped, at least, but there was some heat and smoke damage to the fittings around the upper areas of the engine room, plus firefighting water damage to the equipment here, and in the steering room, boiler room, and incinerator flat. The bulk of the direct fire damage was in the generator, seen here, from a position just outside of the control room. Going in there, we find all 3 generators badly affected. Examining the scene, the seat of the fire appears to be in way of the number 2 generator engine. The exact cause is under investigation still, but it could well yet be another, sadly familiar, example of failure of a high-pressure fuel line spraying fuel onto hot engine parts, such as the turbocharger. Here's the deck head above the number 2 generator. Steel renewals will be required as the deck above has deformed with the heat. And as always, replacing wiring will be a significant portion of the total repair cost. And now, for the fun bit, the relatively new type of story. This 17-year-old container ship suffered the order of $2.5 million worth of damage as a result of a fire that broke out in her scrubber funnel at 2 a.m. in the morning, 2 hours after she left a European port. Scrubbers, or exhaust gas cleaning systems as you know, are necessary retrofits to older vessels to remove particulate matter and harmful components, such as sulfur oxides and nitrogen oxides, from the engine exhaust gases. We saw lots of fire incidents during the installation of these scrubber systems, and here's a case of fire occurring during operation. In this case, the fire was contained within the exhaust gas scrubber process tank, as seen here, where the upper 3 sections external shell indicate the amount of heat that was generated by the internal fire. The radiated heat from the tank, though, did also affect wiring, light fittings, and some structure and paintwork in the vicinity. It would appear that the fire originated in the panked bed filters, which are now broken and deformed. Mist eliminator filters further up the stack have also been damaged by the heat. The cause is still under investigation, and we'll be keeping an eye out for these sorts of casualties and any near misses. Indeed, if you're lucky, Paul Hill may mention problems with these relatively new systems in his New Year review in January's briefing. Now, a few groundings. This first vessel might look like a deck cargo barge, and that is her basic construction, but she is actually self-propelled and described as a deck cargo ship. While on a voyage in the Far East, transporting a full cargo of coal, this 12-year-old vessel received warnings of an approaching typhoon and diverted to seek shelter at what they thought would be a suitable anchorage. Alas, as strong winds and currents increased with the passing storm, the vessel dragged her anchors even with the engines running, and she ended up aground when they had to shut down the starboard engine due to an overheating turbocharger. Tugs and a lightering barge were sent to assist. A breach in the engine room was temporarily sealed, and after lightering of about 2,000 tons of the cargo, the vessel refloated and was towed to her destination port 3 days away for full discharge, and then onwards for repair, where we see her now. Notice that she has been slipped by means of roller airbags and is now supported on blocks. This is a general view of the damaged port side, which suffered most of the grounding damage. Here, we can see heavy indentations of way of the number 2 port side water ballast tank. Similar damage has occurred all along the port side. And here, a better view of the heavy setting up of the engine room bottom plating. Probably about 80 tons of steel renewals required in total. Oh yes, and damage to the port propeller as well for good measure. So at about $1 million being estimated for repairs, this is quite an expensive damage to a small vessel like this, and probably about $250,000 for salvage services as well. And going back to the circumstances of the incident, in cases like this, even with more conventional ships, the question mark about the adequacy of powering of modern vessels compared to the good old days often appears. The second grounding case this month exceeded the $1 million mark. This 11-year-old Handy-Max-sized bulk carrier went aground in the Sea of Marmara while awaiting inspections to enter the grain corridor in the Black Sea to pick up a cargo of maize from Ukraine. She wasn't allowed to anchor because of the traffic in the area and had to stay adrift with the main engine on standby for 8 days. The grounding probably occurred simply due to navigational errors of judgment, yet this cannot have been helped by such long periods of waiting. Hull damages only, thankfully, no damage to the propeller or rudder. Probably about 30 days in dry dock needed though. This third grounding case has a nice wrinkle to it. This 18-year-old handy-sized tanker was in transit off the coast in the Americas when the crew felt ominous vibrations while making a turn. There was no shoal or shallow water at the location on the current electronic chart they were using though. The vessel started to list to starboard with a breach in the number 3 starboard water ballast tank. However, they were able to balance this by ballasting the number 7 ballast tank on the port side and then proceed to a dry dock where the bottom damage was revealed. The interesting part of this is that another of the owner's vessels had run aground way back in 2012 at a location nearby. And when they dug out the old chart from that time, they discovered the shallow area that they had run over this time marked on that old chart, but not on this new one. This is a sobering reminder that the latest version does not necessarily mean the most accurate version in all respects. And this is just going to be a quick skip through 3 of the main engine casualties to finish. The first is a familiar tale, the second a bit unusual, and the third is an eye-watering, considering the cost involved compared to the relatively small size of the vessel. First is this 19-year-old Suezmax tanker that suffered a series of slowdowns due to lube oil system pressure failure in international waters in the Middle East. They just shut down the big low-speed main engine down to investigate and discovered extensive scuffing and scoring to at least 1 crank pin at the crankshaft and at least 3 crosshead pins. Towage to a repair port was necessary, and this added to the cost to grind the crankshaft, with total costs likely to be of the order of $3 million or so, although there are some disputes about the cost of the towage element. Oil starvation causing metal-to-metal contact on the bearing is the usual immediate cause of such damage to bearings and pins. In this case, investigations are still underway to establish the root cause of the loss of lube oil pressure, for which our surveyor is awaiting all the maintenance records and lube oil analysis reports. This 12-year-old handy-sized bulker on a routine ballast passage in European waters suffered main engine shutdown and a blackout while transitioning a traffic separation scheme in Beaufort 9 conditions. She had just sustained several large wave strikes. It was her port engine that had shut down due to a crankcase oil mist alarm. The crew attempted to restart the engine a few times after cleaning the oil mist detector, but without checking the crankcase, which, with hindsight, may be a bit embarrassing for them. But they were in a traffic separation scheme, and it's perhaps understandable that they didn't want to drift into the wrong lane. Anyways, when they did check the crankcase, they found metallic debris from the bearings and reported the problem to the managers. In the end, they had to limp to a repair port on just 1 engine. The damage was found to be centered at just the number 5 unit of the engine. Grinding of the number 5 crank pin to its limits has now been attempted, but alas, cracks and excessive hardness are still present and the crankshaft has to be replaced. Although heavy weather damage to engines is very uncommon, and while investigations into the cause of this damage are still underway, it may be that the precipitating oil mist alarm resulted from the wave strikes that the first vessel experienced. Just to make a link with the final case coming up, we have to note that to remove and replace the crankshaft, they had to cut a hole into the engine room from the aft cargo hold. All other bits fitted through the engine room hatch. Keep in mind that the cost to cut this access route was of the order of $75,000, about 7% of the total repair cost of just over $1.1 million. And yes, you probably guessed it, the eye-watering cost case involves a lovely motor yacht. Not this one, though. While transiting between ports in the Americas, the vessel in question suffered structural failure of the starboard main engine high-pressure fuel oil pump, thereby contaminating the engine's lubrication system with metallic debris. To ensure satisfactory cleaning, the engine will have to be removed to the vessel, as there is insufficient space, as you can see here, around the engine to carry out the work on site. Unfortunately, in this case, that will mean having to cut a hole in the composite side structure of the hull and also remove the starboard generator and other equipment that get in the way. Here's a view of the removal route as yet to be created. Now, I told you to hold on to that figure of $75,000 to create an access route for the crankshaft of the bulk carrier we just saw, which was 7% of the total cost, Well, for this yacht, they are quoting $200,000 for removal and reinstatement, which is nearly 25% of the total cost. And that's it for this month's November cases. I hope you enjoyed it. Now back to Mark. Thank you.
Thank you, Cindy, and thank you, Jasper. I think you'll agree they were both excellent. And unfortunately, given the weather and the industrial action, they weren't speaking to a full room. So I can't thank you both enough for your efforts today. Just to round things off, our next briefing will be on the 12th of January. Here again at the old library. Hopefully more people will be able to get in then. As per usual in January, Paul Hill will be giving a roundup of everything that's gone on in 2022 as we start 2023. That is for this month. Unfortunately, nobody answered the questions correct for last month, so we don't have a bottle of champagne to give out. Not that if anyone had answered it, they'd probably be here on time anyway because of what's been going on today. But we will be sending out feedback forms with the questions, and as always, a bottle of champagne is an offer for anyone who gets those questions right. So thanks once again to our speakers, and hopefully we'll see you all next month.